Hello everyone, my name is Dipanshu and today I'm going to talk about sequential decomposition of mean field games. So there are a lot of real world applications that involve strategic interaction of a large number of players where each player has a private type which that player only observes and it doesn't observe the types of the other players, and the types of the players are evolving dynamically. One such situation is in Lyft and Uber, where people have these private preferences from where and the route situations where they want to go, and they strategically interact with other people in their neighborhood, which determines their own prices and helps them make a decision whether they want to take the ride or not. A similar interaction happens in cyber physical system when there are number of nodes which make these private observations and make a decision to either transmit it to the central authority or among themselves to minimize their own battery, for example. Such sort of interaction can also be seen in renewable energy markets, financial markets, electric vehicle charging, social networks, smart grid, cryptocurrencies, sensor networks, and so on. Mean field games is a very good model to model such kind of interactions. This consists of n number of homogeneous selfish players where n goes to infinity in the limit, and each player observes a finite valued private type xit and is affected by other players through, not individually but through, a mean field population state, which is a histogram of the types of the players at that point of time. And of course, this histogram sums up to 1, as it should. Each player ice type evolve as a control Markov process, where the next state is a function of the previous state, previous action, and the mean field population state. And each player gets a reward as a function of these variables. And every player wants to maximize this total expected reward over a time horizon t. Now, a natural notion of equilibria for this strategic interaction for any finite players is a Nash equilibrium, which is a set of strategies such that no player wants to unilaterally deviate to maximize their own expected reward. However, as I will talk about it in a minute, the mean field equilibria is approximated by Nash equilibria, or rather, Nash equilibria is approximated by the mean field equilibria as the number of players grow large. So mean field equilibria consists of a set of strategies sigma tilde and a mean field state z, such that for any mean field state z, the policy sigma tilde is such that no player wants to unilaterally deviate from sigma tilde. And just to remind you that this sigma tilde is symmetric across all players. So we define two mappings, one a mapping phi such that for any given z, the set of strategies such that the strategy sigma is optimal for that given z. And similarly, we define a mapping lambda from the set of strategies to the set of z such that for any given strategy, how is z updated? And this is given by equation number 7, which is called Fokker-Planck-Kolmogorov equation. So just to recap, phi z represents the set of strategies that are optimal given z, and zt plus 1 is updated given any strategy sigma through the Fokker-Planck equation. So a pair sigma and z is called a mean field equilibrium if the sigma is optimal given the mean field z, and z is derived from sigma using the forward Fokker-Planck equation. And it is shown, as I said before, that mean field equilibria is shown to be a good approximation of Nash equilibria for when the number of players grows large. So in this talk, we're going to assume that players are going to play Markovian strategies in the sense that their actions only depend on the current mean field state and the current type. An equivalent way of looking at this strategy sigma is as follows. Suppose there is a prescription function gamma t such that action at is taken by using this prescription function gamma t on the private state of the player xt, where the prescription function itself is derived from the mean field state zt through a policy theta t, which is given in equation number 8. And it is not too hard to see that these two formulations of the strategies are equivalent. Given this, we can write the Fokker-Planck-Kolmogorov equation, which I stated before, as in equation number 9, where zt plus 1 depends only on gamma t, which is to say that zt plus 1 doesn't depend on the whole sigma, but only on the sigma that depends on xt. So in a short form, I can summarize this uh, dependence on zt plus 1 as zt plus 1 has some function phi of zt comma gamma t in equation number 10. So now I will give you a backward recursive methodology to compute mean field equilibrium, and it goes as follows. So I'm going to define an equilibrium generating function theta t such that for every zt, I will output gamma tilde t, that is the equilibrium gamma tilde t operated at that zt. So in a backward recursive way, we first define the reward to go functions vt plus 1 as 0 at time t plus 1. And from time t and backwards, and for every mean field population state zt, we compute a gamma tilde t such that gamma tilde t is the solution of the equation number 12, where gamma tilde t maximizes the expected reward to go for each player, where the expectation, the argument that is being maximized over is a measure on the action at of the player given xt. However, I do want to point out here that gamma tilde t also appears in the update of zt plus 1. And in there, we use the same solution gamma tilde t as the solution that we are seeking in this equation. So in some sense, at equilibrium, the gamma tilde t that maximizes expected reward to go is also used in the update of zt. And there's a very nice intuitive interpretation of this, which is as follows. That at equilibrium, when everyone else is playing gamma tilde t, then zt plus 1 is updated using this gamma tilde t. And each player's strategy maximizes its reward to go, or equilibrium strategy maximizes the reward to go, and thus satisfies this equation number 12. Given that, now that we have found this gamma tilde t through this fixed point equation, we use this gamma tilde t back into the expected reward to compute vt, and backward recursively we compute these vt's and gamma tilde t's for all zt's. And thus we have defined a function theta t, and the strategies of the players can be defined as sigma tilde t as gamma tilde t at xt, where gamma tilde t is obtained from the theta t we just computed. And this is our main result, where we show that the sigma tildes that we have constructed in this backward recursive way is actually a mean field equilibrium for the game, such that for the zt that I will show how it is derived, no player wants to unilaterally deviate from this sigma tilde, and the zt's are updated using the sigma tildes using the Fokker-Planck Kolmogorov forward equations. We also show a converse where we show that all mean field equilibria can be computed in this way. Thus there always exists an equilibrium generating function theta that satisfies 12 in the backward recursion, such that sigma tilde is defined using theta. Now there's an issue of existence for the fixed point equation for each time t, and we give the following sufficient conditions to show that there always exists a solution for such a fixed point. So we assume that if the reward functions and the state update kernels are continuous functions in zt, then under this assumption, there always exists a fixed point equation, solution for the fixed point equation number 12 for every time t. And the whole argument of the existence is as follows. Under this assumption, it has been shown that there exists a mean field equilibria. And since from our converse, we know that all mean field equilibria can be found using the backward recursion, this implies there always exists a solution for the fixed point equation in time t. Now I want to briefly talk about the complexity of the finding mean field equilibria. In general, it consists of, as I said, the strategies of the players and the mean fields. And for every given mean field, strategies can be computed using the backward dynamic programming or HJB equation in continuous time, whereas the mean field are calculated in a forward Fokker-Planck Kolmogorov equation. So there's a coupling between the backward and the forward equation. And as one can easily see, the space over which the sigma t and zt lie is the cardinality of a to the power times the time t times cardinality of x times cardinality of z. So this space grows exponentially in time. In our algorithm, we are computing these mean field equilibria by solving smaller fixed point equations for each time t. So thus the complexity of finding such equilibria for using our method is linear in time. So there's a huge reduction in the complexity from exponential to linear. And it is as expected in some sense, because what we are doing is we are extending the ideas of dynamic programming to compute equilibria for such games. As an example, we study a cyber physical security system where suppose there are a large number of cyber physical nodes where each node has a state 0 or 1, where 0 represents a healthy state and 1 represents an infected state. And at each time t, or any node can be infected with some probability q if if it doesn't do anything, and if it does takes an action repair, then it is always healthy. It also gets a reward such that the cost, there's a cost of repair which is lambda, and uh, if there are more nodes in the system that are infected, then the rate of that node getting infected is also higher, and that is reflected through this instantaneous reward. Using these parameters for the system, we find these strategies of the players, and we see that they're monotonic. So in some sense, when as the population of the healthy node is higher, then people want to repair, uh, take the repair action. Whereas if there are less number of healthy nodes, more infected nodes, less number of, there's a lesser probability of choosing the action repair. And there's an intuition for this is as follows: that if there are more infected node in the system, people, and the cost of repair is higher, people, it makes sense to not repair, so that because you know that you're going to get infected sometime soon. But if the number of healthy nodes is high enough, then we know that it makes sense for us to take the action repair. Finally, I would like to conclude by saying that there are some extensions that one could consider, where suppose that players do not observe their own types perfectly, and even the mean field perfectly. And in general, all the applications that have been studied in the mean field games, both for the discrete and the continuous time, can be relooked using this methodology, because in literature so far, the, the methodology that is used is this coupling of the strategies and the population state across time. And this methodology gives a way to reduce that complexity from exponential to linear, and that's why it's a powerful way and can be used to relook the applications as well as the theory of the mean field games studied so far. With this, I would like to conclude, and I'll be happy to take any questions.